Hello, thank you for joining me. I know most of you are a little bit tired after this incredible long day. Imagine it's your first day at the office. New boss, new workers, new space, your first assignment. You're a bit nervous because it's the first day. And they give you the first thing you have to do. There's a program that is running at the moment that is connecting to Memcached, and it has a few issues that they want you to help with. This program is experimenting high latency access in this Memcached. It means it takes just too long to get a query back. You have socket exhaustion, my English. Means that at times when you want to retrieve a socket to do this request, there's no any available. And sometimes there is just bugs. You receive a response from the previous request, which maybe some of you have experienced in the past. I certainly did. So they want you to help fix this, and then you start digging into the problem, and you realize that they are working on a scheme on a round robin. Basically, they have a list of sockets open. No, I don't have. OK. So the first request will get the first socket. The second request will get the second socket. And maybe there is a problem with this socket, so it gets corrupted. But the next request will get a new one, and so on, such. And after a while, a bunch of your sockets are in a damaged state. And then you find out that the best way they thought to get this fixed was to increase the number of sockets. And eventually, what happened is it just takes so long to get a good socket. You keep iterating next one, next one, next one. That's the latency. And then that's when you get the mixed responses. And it's kind of like your gut feeling feels this is probably not your first choice when you make a design of a system like this. So then you think, OK, how can I gonna make this right? How can I do? I can definitely do a little better than that. And you think that the best solution is just to rewrite the whole library. But how do you make it more efficient? How do you optimize code running in the wing? And warning, before we start, today we came to talk about how to optimize code running in the BEAM. Some of these cases are OK to do. For others, however, I really ask you to think twice before doing them. Because we're going to talk about things that are going to make the code way more complicated. And complicated code is really bad, no matter what they say. And be dangerous. They're going to prevent the BEAM to work normally. So don't copy-paste these like you copy them from the internet. Just be mindful. With great power comes great responsibility. So use them at your own risk. And when there's something really bad, I'm going to put this sign, the danger, so you keep that in mind. About me. Miriam Pena, I've been doing Erlang since 2006. I work as a staff engineer for a company called AdRoll in San Francisco. I've been there for 5 years. I'm organizer of the Erlang and Elixir meetup as well in San Francisco. That's our webpage. And of course, I'll take advantage of this moment. And if you happen to travel to San Francisco and you want to join us, maybe you want to speak at the meetup, maybe you want to do a seminar or something, please get in touch. We'd love to have you there. And I'm also board of the Erlang Ecosystem Foundation, which you probably have heard of. We have a keynote just in 1 hour here. And I also left some stickers around that room. So you see round stickers with EEF, that's ours. And AdRoll. AdRoll is a company I work for. We are a marketing company, which means we help our customers grow their customers. And one of the ways we do it is by selling ads, and that's called real-time bidding. And basically what happens is every time each of you browses a random web page, there will be an opportunity to serve you an ad. And companies like AdRoll will receive that opportunity, and we'll have some time to decide what's the best ad we can serve you and how much we want to pay for that. If we win, we serve the ad, and everyone's happy. A wise man once said, we should forget about small efficiencies. 97% of the time, premature optimization is the root of all evil. Reliability, readability is more important. However, we should not pass up on opportunities in that critical 3%. And let me explain you why. This is the CTO, my boss, my manager, Valentino. And these are the numbers from AdRoll. We work with 2 billion cookies. That means we track 2 billion cookies. We receive over 2 million actions per second, and each action has to be responded in 100 milliseconds. That's a really, really tight environment. And that's why we care about running our code fast, because we really have a tight deadline on our servers. Because if we don't respond on time, we get penalized, we don't receive more BEAM requests, we don't sell ads, our customers are unhappy, we don't get money. But also because when you run on an environment of 1,000 machines like we do, a 3% savings is a lot of money. You can get an engineer in the Bay Area for that money, and or a party, which is even better. And also, when you optimize the code, you use less machines. We save energy, you burn less code. That's good for the environment. We all are very, very concerned about global warming. So Erlang and Elixir makes concurrency very easy because it doesn't have shared memory or processes in Erlang communicate just as message passing. What does this mean? It really means when we have two processes and the first process wants to send a piece of data, a message, to another, the data gets copied to the other. Simple as that. Of course, there are some exceptions to it with atoms, with big binaries. The code doesn't get copied, literals doesn't get copied since the last release, and so on. But for the most part, this is what is happening. And it's really great because it lets you garbage collection on the process level. So if you kill a process, cleaning up is super easy. But then in terms of performance, it has some trade-offs because all this copy implies a CPU and memory overhead. Some of the ideas we're going to talk today are about improving performance of this concept. Don't make an interpreter allocate memory when you don't have to. You don't have to move data around processes if you can avoid it. Don't create too many processes. Don't use abstractions if you don't have to. Why waste the cycles? And let's go back to our example. We have a Memcached driver. What you would normally do is to have a pool. And that pool will receive a few requests, and everything is happy. The first prototype would be something like this, which is probably something we've all worked with. So the client will ask the pool for a connection. If it has one, it will be returned. Otherwise, it will create a new connection. And this is typically stored on a process. You will have a process that will create the new connection to Memcached, and then you use that process to do the operation to Memcached. So basically, the pool will return the connection, and then the client will use the connection process to send the data to Memcached, return, 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 all happy. Great model. There's nothing wrong with it. Highly recommended and very useful. However, when you have a bunch of requests, the pool becomes a bottleneck. And that's not great. Think about 1 million requests. So what can you do? Well, you can avoid unnecessary indirections on critical components by making the pool faster. Because high-level libraries add unnecessary computation. Basically, don't use a Gen server for that process. Use the process directly, because it's really faster. And this is something we do in AdRoll a lot. We avoid to use Gen servers unless we really have to. We use the verbal processes, sometimes to proc-leaf, sometimes we just spawn it. Especially for high-performance paths. And we can measure how fast this is. And I give you a few tips about measuring. Of course, for a long time, not for microseconds. Don't do it in the shell. Because the shell is interpreted, and when you compile code, it works in a different way. So make sure you put your code in a module, compile it, and run it. We use a library called Ministat that Fred recommended me. I love it. It's really cool. And then if you find a bottleneck, you have a sort of wonderful tools that you could use to benchmark why is that happening and find the right place to make it better. This is the output of a mini-stat, and is basically the left one is for Gen server, the right one is for the proclif, and it gives you average and maximum, and it gives you if you have enough data to get conclusions. But the whole idea here is that if you use the verbal process, you can make 80% more requests, which means you can almost do twice as many requests to the pool to get the data than if you use a Gen server, which is faster. However, hard to read code. So be mindful of that. Have to mention my coworker Brujo is very unhappy about me mentioning this. So he has very strong reasons why you should not do this. So talk to him. But if this is not enough, so the idea is that you should get your socket process as soon as possible. If this is not enough, there's something else you can do so your pool would work faster. And that's changing the process priority of that process. I've seen it, I've done it, probably not my first choice. How this works is basically OS processes have a priority and Erlang processes have a priority too. And every new process will respond with normal priority. However, if this is our scheduler and this is our how each box is a process and organized by the priority, how this would work, of course, is first the max priority process will be executed, then all the highs. And as long as there is highs, no one else will get executed. If they're with more highs, all of that. So that means that no normal, no low will be executed as long as there are processes on high. And that's where it could be an starvation scenario. And that is why this is very, very dangerous. And probably you should not do it. Normal processes get sent combined with low. So a few normals and then a few lows and a few normals and a few lows. So that's OK. And you can also reduce the priority of your processes to low if you want to. And that's OK. Then, again, on your pool, if you focus on how you do the dispatch on your receive loop, there are certain things that that matter. And the first one is the order of arguments in a function to call another function, and then the order of the function arguments. Let's talk about them. And by that, we're going to look at the assembly. Have any of you seen assembly before? Very, very impressed. Good. OK, so we have this function here on the left. You have order ABCD, which calls ABCD plus 1. That's what you should do. You should not reorganize all the arguments around. And I'm going to show you why. Because the first one and the second one have this extra computation about reorganizing them. You see here, moves x3 to x4, x2 to x3, x equals 1, x1 0 to 1, 5 to 0, and then you return. And this is not even one reduction. It's really small. But I doubt I can actually benchmark this. But it's not necessary, so why would you do it? Similar thing with the order of clauses. It used to be said that the order is preserved. It's not as much anymore, but because the compilation knows better than you, and they will reorganize the code for you. But here in this case, you see that the order for binary and list is preserved on one label to the next one. However, in this other example, as first it does a test for its atom, then it will compute the third atom, and then the first atom, and then the same for integer, second number for number. So the compiler will reorganize things to make it more efficient than you thought of them. Right. Let's go on. Or prototype. So we have our pool, which is a process which we did the process, we did the organization of the function clause, we changed the process priority. Now we can do something else. If you notice, every connection is handled by a process. So you have a socket, a process per socket there. And that's probably too many processes running around that you don't necessarily need. So what you could do is to change this model and have the process just create the socket and then hand over the socket to the pool by doing a controlling process on the socket. So this way, of course, you don't want to create the socket on the pool because you will block the pool by doing that. But after this, all interactions with the socket are happening directly on the client process instead of in the process with the socket, which means you save this message passing with the data, which is, and also you save some extra processes that you don't need. And this is something you can do if the socket is passive, which some argue is faster and some argue it's not. You should only do it if you trust your server. And it's also a little bit tricky in terms of parsing because you don't have a lot of things that your server does for you on active mode. But it's worked for us really great. Then you have your socket. There's certain things you can do to send the data through it as fast as you can. Of course, handle binary before lists as much as you can. Use IO lists to concatenate the data. Don't do a list concat. It's not worth it. Use built-in functions and pattern matching when you receive the response as much as you can, because that way you let the compiler do the optimizations for you. And there is an option in the compiler called bin-opt-info that you should definitely use because it will give you some hints of how to get to the next step. And then if this is not enough for you, you can remove a few more of the abstractions, which is faster. And you can go for undocumented, unsupported APIs that can be removed at any time. I've never used this myself. I've Googled it. Some people have mentioned it, and right after say, don't use it, don't use it. But it's there. Apparently it works, and it helps. So you have that option. And the only reason I mention it is because in the next release of Erlang, there's a new library called Socket, which is doing practically the same. The idea is that this socket is implemented as an if and is as close as possible to the OS level socket interface. So it should be really similar in performance to the PrimaNet module. And this is a great excuse for updating your virtual machine version and try it out. Remember, it's experimental. OK. And another design decision we took with our new Memcached driver was related to the thing that one pool was just not enough for us. We needed to have several pools per Memcached server to make it work. And then we also had to have a sharding mechanism because we have to have several Memcached servers. And then it became this crazy configuration to decide from a request to which of the pools we go to. And we have this crazy configuration in the state. And then we were like, how do we get this very fast, very efficiently from every process? And that's why we started experimenting with low memory CPU footprint key value storages. When you think about low memory CPU footprint key value storages, what's the first you think about? Good. But just before you think about the ETS, and then you think, no, not enough, not fast enough. Why not fast enough? Because the bigger the ETS, the slower it gets to get the data. The bigger the data, the slower it gets to copy it back to your process. But if you have, if you just say you have this argument that you want to pass around in every single function, but you don't want to do that because it's kind of annoying to have this argument in every single function of all of your program on your process. Some people will suggest to use an ETS table, but forget about it. Process dictionary is really much faster. This is how you get what's on your process dictionary. You go process info with a key dictionary. And as you see, it's used for ancestors. It's used for initial calls. Is also used for the random for a seed. Another library is used for global key value cache. So it's you're using it all the time, even if you don't notice. And I benchmark this. Of course, I choose to, I think I have a process dictionary with one key and an ETS with one key. And what I benchmark is to change the value of the data I'm storing. And because I want it to be copied, I put a tuple there. So I play with tuples of very different sizes. And when the size of the tuple is 1, it's 200 times better, which means it's twice as fast. So you can do 2 process dictionary lookups for the price of 1 ETS. But as the tuple gets bigger, it gets madness. It's really crazy, like 6,000 times better for a tuple size of 10,000 elements that you will never do because no one in his right mind will do ever a tuple size of 10,000 elements. You put it on the dictionary or a tree or something. But yeah, so it's really, really faster. This is how you do it. Put, get, very simple. And of course, be really mindful. If you hide the state, you're breaking, you create side effects, and bugs will be really hard to track, impossible to track. And I really recommend you to Google about this. And there's a lot of articles which explain why you should or should not do this. Next, what happens if you want to send the data between processes? You want to have key value stores that you can access between several processes. Up until recently, and this is what we actually did on our driver, our Memcached driver, was to use code generation. The idea is that if you have a big configuration, like a term with a lot of things, that if you want to pass to another process, you have to copy, that takes time. So maybe a way to avoid copy is to put that code in a module, compile the module, and call a function that returns that piece of data. And that is not copied, that is reference, so it's great. It's faster, and Mochi Global, Fast Global lie on that idea. We did the code generation ourselves when that did. This is kind of the model. You have like a configuration systems which indirectly send you to the right pool. But the great thing is that in the 21.3, right? Yeah, 21.2, they introduced something called persistent term, which is practically something that does the same. Let's talk about it. The idea is you have a piece of data that you're going to just write once or once in every long time, like days. And you're going to read it very, very frequently. If you need it to be fast, with no logs, no copy to the heap, you can use this module called persistent term for that. And that will be extremely fast. Again, the problem with this is that every time you write, if what you write is bigger than what you have, you're going to trigger a global garbage collection, I believe. So it's not designed for that, but it's really great for global configuration, for instance. And we benchmarked how great it is. ETS lookup of a key through a persistent term get. The environment here was having 1,000 elements on the ETS, 1,000 elements on persistent term. And again, I played with the tuple size. With one element in the tuple, you get twice as much requests with persistent terms. But as it goes up, it's way faster. 264 persistent term lookups at the same price as one ETS lookup. Super interesting. And if this is not enough, we have 2 new cool boys in town to operate hardware level as well since 21.2. I was so excited when Lucas told me about this. So these are low-level hardware atomic instructions with no locking, no costs. They work with 64-bit integers, and they let you do operations on arrays of that fixed size of 64 bits. Counters instant extraction on the top of atomics, which is I'm actually very familiar with. And the typical usage will be, instead of using an ETS update counter, like if you have a counter, you need to increase a value, 1, 2, 3, or +2 over 10. You could traditionally do ETS update counter. Now you can do a counter add, and that will be super fast, low level. Again, there's 2 ways to work with this, with the counter. The default one is through atomics, which is what you expect from a counter. Like if you do operation A and operation B, any reader will read A or B, but they will not read only B. You follow me on that? No? So if you do write operation A and then operation B, a reader will see one of the operations, none of the operations, or both, but they will not see B on the isolation without A. That's atomic. If it's OK to see B without A, then that's write concurrency. I picture this case as, for instance, in our case, when we spend money on an ad and you want to keep track of how much money you spend on a certain campaign, we don't really care if one ad is counted before the other. We just want to eventually both be counted. And I think that's when write concurrency would work for us. So this is with concurrency. So with one worker, which means no concurrency, counters is 85% faster than an ETS. But as the number of workers increase, and somewhere my number of CPUs hit, and it's probably where it gets, it could be 60 times, 66 times faster to use write concurrency with a counter than to write an ETS directly, which is really mind-blowing. And when all this is not enough, there's something you all can do. What is it? NIFs. You can just write the code in another language, which is a little bit more designed for the computation you want to do. It should be an emergency pool. It's a little bit dangerous because, well, if the NIF takes too long to run, it can really trick how the scheduler balances the work. So you have to be very mindful of how long it takes to execute a piece of code, maybe send in a batch. So you do this little bit, and get back the control to the virtual machine every now and then. And also, just because you put it on a NIF doesn't mean it's faster. So you have to also optimize that part. We use it a lot for Jiffy, for JSON, but for others as well, for Go. And of course, extremely memory usage. We had actually leaks on NIFs which were really hard to track. So last resort, but it works. So in the end, the time it costs to analyze a strategy A versus strategy B is really high. And when we do most of the optimizations, we don't really benchmark every little thing we do. We do like everyone else. We put our code in production and see how it goes. And that's what we did. On Valentine's Day, I was testing OTP 20 versus OTP 19. This is a CPU usage, one of our servers in production. And you can see, just by changing the Erlang version, we save 20% CPU. And I know this is probably not mean that it's 20% faster, because there's a lot of factors. But it's a good sign. A little bit later, that's last month, I think, we changed to OTP 21, and we got another 10% on CPU. But this time I knew better, so I actually graphed the scheduler usage. And you also see, I don't know, maybe it's like 10, 15. That's how it changed. But really, with a scheduler usage of 20 or 25%, it's not really stress, so it's hard to tell. So I decided to stress the system. So I created a staging environment, and I put a bunch of load over there. I put the machines on 99% CPU usage and 99% scheduler usage, and see how many requests were served by each version. And here you see an OTP 21, I think it was 10 times more requests. That's the blue line above. That's 8,000 on average. 8.67 thousands versus 8. That's a little bit 12% probably better than OTP 21. This is for a specific machine, but it's great. Thank you, thank you, thank you. That's a few $1,000s a month. So if there is only one takeaway I want you to bring with you today, is go back home and update your virtual machine version. Forget about the rest, not worth it. Okay. So our driver, our Memcached driver, ultimately, I did it. The performance was really great. I think we got a request in less than 1 millisecond, 0.7 milliseconds. That was like 4 times less than before. So I got the job. I got to keep my job. And then we open source it on GitHub, and it's also in X. If you want to use it, we use it massively for reading our users, for doing lots of operations in every request. And I want to finish this talk remembering 95% of your code is only run 5% of the time. So there's no really point of optimizing code before you benchmark and figure out what that 5% of the code is. So premature optimizations will likely make your code very unreadable. It will be hard to maintain. And you should really focus on clarity and expression. But if in spite of this, you decide to implement the things I talk about today, there is another second piece of advice I can give you. You should hire someone else to take over your code and leave your company. Thank you.
All right, time for some questions. No questions? Victoria.
So you mentioned that you really like benchmarks, and you mentioned tools that you use, and so what was the very favorite tool that you used?
I benchmark in production. That's my favorite tool. What I do, I could lie, but it's not the point. So what we normally do in every release is to launch 1 or 2 or 3 machines of our new test release, and then another 2 or 3 of our current release. We launch them at the same time. We leave them running for hours or for days, depending on how concerned we are. And then we measure how one operates over the other. So if it has more requests, if it has a CPU performance, has a memory performance. At the scale we're working and at the speed we're working, we can't really afford to go very, very deep unless we have a critical issue, which we have had, and then we did in some scenarios. Yeah.
Thank you.
All right, it's living dangerously. Anyone else? All right, let's break. Next talk is at 5:15.